We've seen that making a solution affects the vapor pressure of the solvent and the solute above the solution. Since pressure and temperature for a phase change are intimately linked, it's reasonable to expect that the phase change temperature, boiling point or melting point, would also be affected by solute concentration. Let's see how this works. When a substance melts, the solid and the liquid are in equilibrium. When a substance boils, the liquid and the vapor are in equilibrium. Since two phases in equilibrium have equal chemical potentials, understanding how the chemical potential changes with temperature should help us answer our question. Remember that the chemical potential changes according to the temperature at a given pressure as the entropy, the opposite of the entropy. And so the slope of our chemical potential versus temperature curve is going to be equal to the opposite of the entropy. So the slope will be negative, and the value of that slope will be equal to the entropy of the substance. At low temperatures, we expect to have a solid. Solids have very small entropies, and so we expect the slope of the chemical potential versus temperature to be shallow. At the melting point, we will form a liquid. A liquid has a higher entropy than the solid, and so at that point, the slope will increase. At even higher temperatures, we form a gas. A gas has the highest entropy, and therefore we have an even steeper slope for the gas. Below the melting point, the substance will exist as a solid. However, we can still assign a chemical potential to the liquid and to the gas phase below the melting point. If we simply extend the melting point line and the vapor chemical potential, we can see that at temperatures below the melting point, the chemical potential of the solid is lower than the chemical potential of the gas or the liquid. This is why our substance will naturally occur as a solid at temperatures below the melting point, because systems always tend towards lowest chemical potential. And thus, the spontaneous direction for a phase change at temperatures below the melting point is to form the solid. Likewise, at temperatures between the melting point and the boiling point, you can see that the liquid has the lowest chemical potential, and so the spontaneous direction is always to form the liquid, and thus substances exist as liquids between their melting and boiling points. Finally, at temperatures above the boiling point, the gas phase has the lowest chemical potential, and that is the phase which will naturally exist at temperatures above the boiling point. Our original question had to do with what happens to the melting point and the boiling point when we add a solute to our pure system. To answer this question, let's look at the chemical potential of the solvent when we have a solute. Remember that the chemical potential of the solvent is equal to the chemical potential of the pure solvent plus a correction for the solvent not being pure. And that correction has to do with the natural log of the mole fraction of the solvent. The chemical potential of the pure solvent is what we've graphed here. If we want to look at the chemical potential of the solvent in solution with a solute, then we need to see how the chemical potential of the solvent in solution varies with temperature. Notice that because x is always less than 1, the natural log of x will always be less than 0, and therefore we are subtracting a correction from the pure chemical potential, and so the chemical potential of the solvent in solution will always be less than the chemical potential of the pure solvent. Thus, our chemical potential for our pure solvent, which is shown here, is greater than our chemical potential for the solvent in solution. And so we get a line for the solution which is below the pure solvent. When a solvent freezes from solution, the solid that is formed is nearly pure solid. Therefore, the chemical potential that we're interested in for the solid remains the same as the pure solid line. Notice that the chemical potential of the solution and the chemical potential of the solid now are the same at a much lower temperature than the pure solvent. So the melting point of the solution is depressed or lowered over the melting point of the pure solvent. Thus we say that we have melting point depression in a solution. When we have a non-volatile solute in our solution, the vapor phase will be pure solvent. And so again, the chemical potential we're interested in for the vapor phase, for the gas, is the same as the pure solvent chemical potential. And now we can see that the solution chemical potential and the vapor chemical potential are the same at a much larger temperature than the pure solvent, and so the boiling point of the solution is elevated relative to the pure solvent. So we have boiling point elevation and freezing point depression when we have a solution.